In the vast expanse of our universe, few cosmic entities capture our imagination quite like black holes. These gravitational behemoths, born from the catastrophic collapse of massive stars, represent the ultimate cosmic mystery, regions where the very laws of physics as we understand them break down completely. I'm Alex McColgan, and you're watching Astrum. Today, we're going to venture toward one of the most perplexing questions in modern astrophysics. What exactly lies on the other side of a black hole? When we gaze into the night sky, we're looking at light that has traveled unimaginable distances to reach us. Light that has navigated around galaxies, through nebulae, and across the vast cosmic web. But when light encounters a black hole, something extraordinary happens. It simply doesn't escape. This absolute capture of light gives black holes their name and their mysterious character. It's their defining characteristic, and it's what makes the question of what lies beyond them so tantalizing. Black holes are where God divided by zero. The physicist and science communicator Neil deGrasse Tyson once quipped. And there's truth in this humor. At the heart of every black hole lies a singularity, a point of infinite density and zero volume where our current understanding of physics simply falls apart. But to truly understand what might be on the other side of a black hole, we first need to grasp what happens when you approach one. Let's imagine you're an astronaut on the ultimate mission of exploration. Your spacecraft is somehow engineered to withstand extreme gravitational forces, and you're heading straight for Sagittarius A, the supermassive black hole at the center of our Milky Way. As you approach, you'd notice nothing particularly unusual at first. Black holes don't suck matter in like cosmic vacuum cleaners. They attract matter through gravity, just like any other object with mass. If you replaced our Sun with a black hole of identical mass, Earth's orbit wouldn't change at all. The difference is what happens when you get close. As you venture closer, you'd eventually reach what astrophysicists call the event horizon, the point of no return. This boundary marks where the escape velocity exceeds the speed of light. Cross this threshold, and even light itself cannot escape the gravitational pull. It's a one-way journey inward. This event horizon isn't a physical surface you could touch or land on. It's a mathematical boundary in space-time. And this is where things get truly strange. From your perspective as our intrepid explorer, crossing the event horizon might not seem immediately catastrophic. In fact, according to General Twytheat's relativity, you wouldn't experience anything special at that exact moment. You'd continue falling inward, still able to see the universe behind you, distorted into an increasingly small circle of light as the black hole's gravity bends the incoming light around you. But there would be no sign saying, "Welcome to the event horizon." No physical sensation marking your passage beyond the point of no return. But for an observer watching from a safe distance, your journey would appear quite different. As you approach the event horizon, they would see you moving more and more slowly, your image reddening and dimming due to the extreme gravitational redshift. Time itself appears to slow down near the immense gravity of a black hole, an effect known as gravitational time dilation. From the outside perspective, you would appear to freeze at the event horizon, never quite crossing it. This discrepancy between what you experience and what an observer sees is one of the fascinating paradoxes of black hole physics. Once past the event horizon, your fate is sealed. The singularity awaits. All paths in space-time point inexorably toward the center. This is a bizarre concept to grasp. Inside the event horizon, moving away from the singularity would be like trying to move backward in time. It's not just difficult, It's impossible within our understanding of physics. As you continued your journey inward, you'd experience what physicists call spaghettification, a rather whimsical term for an utterly devastating process. The difference in gravitational pull between your feet and your head would become so extreme that you'd be stretched vertically while compressed horizontally, like cosmic pasta. For stellar mass black holes, this process would begin well before reaching the event horizon and would tear apart your spacecraft and your body long before you could record any meaningful data about what lies beyond. But what if you somehow survived this journey to the center? What would you find? This is where our current physics reaches its limits, and where some of the most fascinating theoretical possibilities begin. The simplest answer, based on general relativity alone, is rather anticlimactic. There is no other side. The singularity represents the end of space-time itself. All matter that falls into a black hole is crushed into this infinitely dense point, where the laws of physics as we understand them simply break down. Space and time cease to have meaning at the singularity. It's not so much a place as it is an end to the very concept of place. But physics abhors infinities, and many scientists believe that a more complete theory of quantum gravity will eventually resolve the singularity problem. This is where things get speculative and fascinating. One intriguing possibility comes from a theoretical extension of general relativity known as the Kerr solution, which describes rotating black holes. Mathematically, these solutions suggest the possibility of what's called a white hole, essentially the time reverse of a black hole, where nothing can enter but matter and energy can exit. Some theoretical physicists have proposed that black holes and white holes might be connected, forming what we call a wormhole or Einstein-Rosen bridge. Wormholes, if they exist, could theoretically connect two separate regions of space-time. Picture a tunnel through higher dimensions that creates a shortcut between distant points in our universe, or perhaps even between different universes altogether. The mathematics of general relativity doesn't rule this out. However, natural wormholes would likely collapse instantly unless supported by some form of negative energy or exotic matter. Hypothetical substances with properties that seem to defy our current understanding of physics. This brings us to one of the most mind-bending possibilities: black holes as gateways to other universes. This idea has been popularized in science fiction, but it has real theoretical underpinnings in concepts like eternal inflation and the multiverse theory. If our universe is just one bubble in a vast multiverse, perhaps what we see as a black hole singularity is actually a connection point, a cosmic umbilical cord linking our reality to another. Another fascinating possibility comes from loopy, quantum gravity, a theoretical approach that attempts to merge quantum mechanics with general relativity. In this framework, space itself has a discrete quantum structure. When matter collapses to form a black hole, it reaches a maximum density and then bounces back, creating what's called a black hole to white hole transition. Rather than ending in a singularity, matter would be ejected into the same universe, but in a different region of space-time. Stephen Hawking's groundbreaking work on black holes adds another layer to this cosmic puzzle. In the 1970s, Hawking demonstrated that black holes aren't entirely black. They emit a faint radiation now known as Hawking radiation. Over extraordinarily long timescales, this radiation causes black holes to lose mass and eventually evaporate completely. This raises profound questions about the information that falls into black holes. Quantum mechanics insists that information cannot be destroyed, yet black holes seem to erase it. This information paradox remains one of the most significant challenges in theoretical physics. One proposed resolution to this paradox is the holographic principle, which suggests that all the information about matter that falls into a black hole becomes encoded on its event horizon, like a three-dimensional image stored on a two-dimensional surface. In this view, nothing truly crosses to an other side in the conventional sense. The information is preserved at the boundary. Recent advances in theoretical physics have led to even more exotic possibilities. Some string theory approaches suggest that black holes might be dense collections of fundamental strings. Others propose that the singularity might be replaced by a fuzzball, a tangled ball of strings with no actual singularity at its core. In these models, there might not be an inside to the black hole in the traditional sense at all. The 2020 Nobel Prize in Physics was awarded partly for work on black holes, recognizing Roger Penrose's mathematical proof that black hole formation is a robust prediction of general relativity. This underscores how central black holes have become to our understanding of the universe. Yet, despite their importance, the ultimate nature of what lies at their core, or beyond them, remains elusive. What makes this question so compelling is that it exists at the intersection of our most successful physical theories, which nevertheless seem fundamentally incompatible at the extreme conditions of a black hole. General relativity, which describes gravity as the curvature of spacetime, breaks down at the quantum scale. Quantum mechanics, which governs the behavior of subatomic particles, doesn't fully account for gravity. Black holes are cosmic laboratories where both theories must somehow be reconciled. Observationally, we've made remarkable progress in studying black holes. In 2019, the Event Horizon Telescope collaboration captured the first direct image of a black hole's shadow, specifically the supermassive black hole at the center of galaxy M87. This stunning achievement confirmed predictions from Einstein's theory of general relativity and gave us our first visual glimpse of these extraordinary objects. In 2022, they followed this up with an image of Sagittarius A, the black hole at the center of our own Milky Way galaxy. We've also detected gravitational waves, ripples in space-time, produced when black holes spiral together and merge. These observations, first made by the LIGO and Virgo collaborations in 2015, have opened an entirely new window on the universe and provided compelling evidence for black holes with masses ranging from a few times that of our Sun to dozens of solar masses. Despite these observational triumphs, the interior of black holes, and what might lie beyond them, remains hidden from direct observation. The event horizon ensures that no information from within can reach us. This observational barrier means that theories about the other side of black holes remain largely in the realm of mathematical physics and theoretical speculation. It's worth noting that while I've been speaking about crossing the event horizon and journeying to the other side, the reality would be far more brutal. For stellar mass black holes, tidal forces would tear apart any physical object long before reaching the event horizon. Only in supermassive black holes, where the event horizon is much further from the singularity, could you theoretically cross the boundary intact, only to face the inevitable journey to the center. Perhaps the most profound aspect of this question is what it reveals about the limits of human knowledge. Black holes represent the boundary not just of space-time, but of our current understanding of physics itself. They remind us that despite all our technological and theoretical advances, there are still fundamental mysteries in the cosmos. Some physicists have even suggested that the question of what's on the other side of a black hole might be inherently meaningless, not because there's no answer, but because our concepts of space and time break down so completely that the notion of sides or beyond loses coherence. In this view, Asking what's on the other side of a black hole might be like asking what's north of the North Pole. Yet the human drive to explore and understand persists. The same curiosity that led us to venture beyond the horizon of our flat Earth, to probe the depths of our oceans, and to reach for the stars now compels us to ponder what might exist beyond the boundaries of known physics. Whether black holes lead to other universes, connect distant parts of our own cosmos, or simply, and in a singularity that defies comprehension, they represent one of the greatest frontiers in modern science. The quest to understand them forces us to stretch our minds, to reimagine the very nature of reality, and to push the boundaries of what we thought possible. As we continue to observe these cosmic leviathans with increasingly sophisticated instruments, and as theoretical physicists work to resolve the apparent contradictions between our most successful theories, we edge closer to answers. The journey to understand what lies on the other side of a black hole is not just a scientific endeavor. It's a philosophical one that touches on the very nature of existence itself. I'm Alex, and thanks for watching Space Truths. If you enjoyed this journey to the edge of known physics, don't forget to like this video and subscribe to our channel for more cosmic explorations. And if you'd like to support the creation of more content like this, consider joining our Patreon community through the link in the description below. Until next time, keep looking up and wondering what lies beyond.